he has very beautiful ideas and very much elementary, except you have to use the basic property of the real numbers. So Allergan wrote the paper 1814, and later Cauchy also it seems independently the proof, but his argument is basically in the following three steps. First is any the polynomial. So fx is a continuous function on the complex number C, on complex plane C. Not real, but complex numbers. And continuous means that that's okay. Continuous means if you take
But does this notion of continuity exist in his era?
Yeah, that's a yes. And I think he in this way, I think he understands. But of course, to define precisely what this means, you really need to use the epsilon delta method. So it's already at almost the end of the 19th century that they really understand what continuous function means. But very rough idea is something like that. If the point goes to tend to some fixed point, then this value goes to this point. And can you prove it? Yeah. It probably is a quite good exercise for the graduate and undergraduate student. Okay, so this we assume. And second is really important fact. Is if you take this complex plane, the compact set, so it's a closed finite region. Domain or region. Actually, enough. In our case, enough constant case. So it's just a closed. Closed disk. That's all. And the compact, if you take any compact set, if f is continuous function, then real functions. And so maybe it's better to change it. G is a real continuous function. Then G has a minimum. some point A in K. So in other words, if you consider Enchman of Fz, Z in K, G, then there exists some point A which really attains. This is the most important factor about real functions, continuous functions. Real values. This is the topics of the elementary calculus, but usually the proof is not so easy. It really depends on the property of the real numbers. So actually the algorithm assumed this. I think he couldn't prove it. Okay. And then finally, it's a very interesting thing is what he used is any complex number alpha has at least one case root in C. So I think that's in this way is inside of C. That we already know that, because if alpha is written by something like cos theta 0 plus I sine theta 0, the one possibility is just taking that L. This is well defined, this is real number, case root, and then cos of theta 0 k plus I sine theta 0 k. This is one of the case root of alpha. If you take the case power, then it becomes alpha. So actually the algorithm assumes these three facts. And of course 1 and 3 would be not so difficult, and the only difficult part is this part. And this is the sort of the achievement of the 19th century real calculus.
Did he give proof for these three factors?
Pardon me?
Did he give proof?
No, he didn't prove actually. He used this part. Okay, so now let's start the proof of this fundamental theorems. Okay. Okay, so let's start F. Or maybe A0 is not important, so okay. So what you prove is just consider the absolute value of this fz and take an Enchman objective C, then you need to show that there exists certain number C. So this polynomial has always minimum value in somewhere. And then later I will show that this minimum value should be 0. So that but first, and this is very simple because just consider the following. Fz we can write in this way: Gn 1 plus. So I write HW is A1W plus HW square plus ANWN. Okay? Then it should be then of course use this one. It's okay?
And one next in the second equality.
Yeah. This part or this part?
About.
Yeah.
Here.
Just divide by.
But there should be a bracket.
Oh, sorry. You are right. I'm sorry. One part. Yes. That's okay? Okay, now HW. This HW is of course continuous function and H0 is 0 because it starts from the W1 term. So there exists